possibility to give this talk. So I like colors very much, so I hope you don't mind. I would like to start by taking a scaling limit already, because the workshop is about conformal invariant scaling limits. And this is a scaling limit approach to the Gaussian free field, which I wasn't aware of beforehand. It came up for me in discussions with Jean-Christophe Murat and Scott Armstrong, among other things we discussed. So what you do is you just take the grid, for example, the triangular grid. It has mesh size 1/n here. On each edge, you put a ID random variable. You say unit variance means 0. And you consider it as a flow on the edges. Now, what you do is you take the discrete divergence of this vector field, and you get a random field on the vertices, say rho n. What's next? Now you just want to say what's the scalar potential actually corresponding to this charge field. And for this, you solve the discrete Poisson problem with Dirichlet boundary conditions. Then you again get a random field on the vertices. You interpolate it linearly. And when the claim is, it's the fact that as the mesh size goes to 0, these random fields you find will converge in the space of distributions to the Gaussian free field. So I call it the Donsker for the Gaussian free field because it is really the multidimensional version of the Donsker's invariant principle in one dimension. Now, we won't use it, but I wanted to introduce it because I find it nice. And on the other hand, it's as a little psychological standpoint. Every time I become afraid of the Gaussian free field, I come back to this and to say, oh, it's actually a friendly object. We will be interested in the couplings of the Gaussian free field with the SLE lines and the geometric couplings. The first one is the contour line coupling, which was already introduced by Ha Wu yesterday. And how does it go? Well, there is a coupling of the Gaussian free field and the SLE4, such that to sample an instance of the Gaussian free field, you can do the following. For example, on there's something wrong here. I will comment on this. So on the upper half plane, you first sample an instance of the SLE4, and then you just sample a Gaussian free field in the slit domain with boundary conditions. And this boundary condition should be minus lambda left to the curve and lambda right to the curve. And on the boundary as well, it's actually minus lambda on the negative real axis and plus lambda on the positive real axis. So it comes out that this SLE4 is then measurable with respect to the Gaussian free field, and it looks more or less like this. So this is the theorem from the paper of Shum and Sheffield. And why do we call it the contour line? Because actually we can see that even if in the continuum the Gaussian free field is a rough object and you can't really give it a geometric meaning, then in the discrete Gaussian free field you can really define a level line, and you can see that these level lines will converge in the coupling to the SLE4. So this is the one coupling we are using, and the other coupling is a flow lines coupling, and we are just using a baby version of it, a very restricted version. And this is a coupling in this constant just between the SLE kappa with kappa less than 4 and the Gaussian free field. How does it work? It's very similar. You can again sample an instance of the Gaussian free field by first taking the instance of the SLE curve, then taking the Gaussian free field in the slit domain with boundary conditions again, minus lambda to the left, lambda to the right. Again, on the real line, there's no chi times v term. So with the flow lines, there is one additional factor. You have to add another harmonic term to correct for the to really get a Gaussian free field. And this correction term is related to the winding. So it's related to the argument of the derivative of the uniformizing map. Again, these curves are measurable with respect to the Gaussian free field. And this coupling was first, I guess, envisioned by Scott Sheffield. Then Dubada showed measurability. And now Miller and Sheffield have built a whole theory out of it, where they consider different SLEs with kappa also bigger than 4, SLE kappa rows, and they get really beautiful pictures. So they get pictures where you have several flow lines interacting, and And these are just nice to show to even to your mother. In this talk, I would actually like to take a slightly different viewpoint on this coupling. I would like to ask whether we can get any information about the Gaussian free field using these couplings. Can we say something about the Gaussian free field we didn't know beforehand? Well, this is a very loose question, and I'm actually not entirely clear how to make it precise. But I guess what I have in mind is that, if you look at the Brownian motion, for example, the first time it hits a level, you can say that locally, if you look backwards, it looks like an upside-down Bessel process. And how do you make sense of this in the Gaussian free field case? Well, one way would be to look at the circle average process. So what is the circle average process? Well, you can't look at the field at a fixed point because the variance is infinite, but you can look at the epsilon circle around a fixed point. You can put unit mass on this epsilon circle. Then you can test it against your Gaussian free field, and this will give you just a Gaussian random variable which has more or less variance minus log of the radius of this circle. And now you can actually start changing the radius of this circle and ask how does it look like as a process. So it comes out that if you take a point in the bulk, then this process is really a Brownian motion. Now what happens if you take a point on the boundary? Well, if you take a point on the boundary, still of zero boundary Gaussian free field, then you can see that it's actually, the process will be stationary. If you again, you parameterize it by using minus the logarithm of the radius, then it will be stationary, it will be Gaussian, it will be Markov, so it's more or less like a Ornstein-Uhlenbeck process. So you can see it's very different. What I would like to say is ask is what happens when you do the same thing on contour lines or flow lines. So I guess with contour lines it's rather clear. So how was the coupling? The coupling said that on a contour line you more or less put a boundary of the Gaussian free field. You just have to sample the Gaussian free field in the slit domain. So this hints that it will more or less look like an Ornstein-Uhlenbeck, where the variance doesn't grow if you look at the circle average process. And what about flow lines? Well, there I can't make it really precise, but it seems that it will be, again, a Brownian motion, but just with variance that's much smaller. However, I want to make some of this precise. So how do I do it? I do it in a slightly intertwined way. I will actually look at the exponential of the Gaussian free field, or the Liouville measure, and show you how in that context I can really tell you what happens on the flow and level lines. So the next chapter is the Liouville measure and also the KPZ relation. So by the Liouville measure, what do I mean? Here I really just mean the exponential of the Gaussian free field, not the more complicated version that was introduced by Rémi Rode yesterday. I mean it in the sense that it was written and defined by Duplantier and Sheffield in their paper. And I guess the exponential of the Gaussian free field we already knew how to define in the 80s by the work of Gahan, but he wasn't really interested in the Gaussian free field, and taking the real Gaussian free field became interesting with the work of Duplantier Sheffield. So I will actually follow their approach in also defining the Liouville measure. So what do you do? Again, you can't take the exponential straight away, so you first regularize your field. There are many ways of doing it. Here I will use the same circle average that I used before to describe the behavior at a fixed point. If you take circle averages, you will actually have a nice continuous field, so you can take the exponential of it. Well, you see that then the mean of this field will be quite high, so you will renormalize for this behavior so that it would have unit mean at all points. And then when you let the renormalization parameter go to 0, you will see that these random fields converge to a random measure. That's called the Liouville measure. There's also this picture, usually that's shown also from the paper of Sheffield and Duplantier, where here each square actually has the same Liouville mass. So what's the equivalent of the question I was asking beforehand for the Liouville measure? The question of how the circle average process behaves. Loosely, the circle average process will correspond to looking at the scaling of Liouville mass, looking at the scaling of Liouville balls around the fixed point. And it comes out that the scaling is given by somehow the following formula. Here, so what are all these terms? Well, R squared just means that you are actually shrinking in kind of Euclidean sense as well. The gamma squared over 2 gives you kind of the change in the renormalization term. And then the last one is really the circle average. Using this, you can, for example, determine the moments of Liouville balls. Say here Q is smaller than 1. And in the bulk, you see that you have the following behavior. Here, really, the first 2 terms correspond to the powers of R, and then the last term you get by just taking the exponential moment of the Gaussian. So you can ask for the same thing on the boundary. And there you see that your Gaussian now doesn't have growing variance, it has actually stationary variance, and then you lose the quadratic term. So this is now something I can make precise on flow and level lines as well. On contour lines, the scaling of Liouville balls in the sense of moments is exactly the same as on the boundary. And on the SLE kappa flow lines, you can see that there is a term that corresponds to somehow diminished variance. I would maybe also want to give you kind of one heuristic about how we can think of the scaling in the bulk. So the Gaussian free field is defined using at least a zero boundary Gaussian free field using the zero boundary Green's function, but it doesn't really, there's a logarithmic term and then there's a correction term that makes it 0 on the boundary, but that term is really nicely behaved, and if you look at the scalings, then it doesn't really matter. So suppose we can consider actually just the logarithmic kernel. So what happens to this logarithmic kernel when we scale things? When we now look at we looked at the unit ball, and now we look at the ball of radius r, and we want to reparameterize it as a unit ball. You can see that the kernel is more or less the same, plus an additive term. And now if you think in terms of Gaussian fields, what does it mean? It means that you have your initial field plus an independent Gaussian random variable which has just variance log of 1 over r. And if you put this in, you will actually really make a specific Gaussian calculation and get the scaling of the balls as on the previous slide. Now, the scaling of Liouville balls can be also given a slightly fancier context than that. This fancier context is called the KPZ relation. And again, I will actually give you a very simplistic view on that. It's the actual physics, what's behind it, I don't understand very well. So for me, intuitively, what is this KPZ relation? Well, you pick your favorite, statistical physics model, say percolation. First, you look at it on the Euclidean lattice, and you calculate some critical exponent, for example, say the one-arm exponent. Well, then you take your model, and you put it on a very, very large random planar map. And now you ask the same question. I ask for the critical exponent of the one-arm event, for example. And then the KPZ relation, stemming from free physics, is Kishnik, Polyakov, and Samolochikov, should give you a quadratic relation between these two exponents. Now, we are still quite far from understanding this in detail, but in any case, already in the physics literature, there's also a continuum form, and this continuum form of the relation should actually use the random metric space that everyone is looking for with its conformal structure. This we cannot do for the moment. But what was a key insight from Duplantier-Sheffield was that we can do something in that spirit at least. We can do something using the Liouville measure. So what is this something we do? Well, we take just a fractal set. We look at the fractal dimension of this set in the Euclidean sense, and now we look at this fractal set through the Liouville measure. And we define a quantum dimension using the Liouville measure for this set. And the KPZ relation will then just relate these two exponents. In this context, there is not just one KPZ relation. There are many corresponding to the fact that there are many ways of making sense of this quantum dimension. So I guess the first one was kind of by Duplantier and Sheffield, where they defined some sort of quantum balls using the Liouville measure. Then there was a version by Remirod and Vincent Vargas, where they used Euclidean balls, but they looked at how the Liouville measure scales in these Euclidean balls. Well, later on there has been a version using the Liouville Brownian motion. You define a sort of Brownian motion on the Liouville measure, and you measure your sets based on how long it, for example, takes to get out of the set or to cover the set. There's a version by Nathaniel Berestisky, there's a version by Carban Remirod, and now there's again a Liouville heat kernel version. So what characterizes, these versions coming on is that we understand the Liouville measure better and better, and we actually use more and more intrinsic or more complicated properties to define the sizes of the sets. But you can also go in the other direction. You can say that, okay, let's try to find the simplest possible way of making sense of the KPZ relation. And I think the simplest possible way is to use a certain expected Minkowski dimension. And why do I say it's the simplest? Because here we will really use the simplest possible phenomenon of this multifractal behavior of the Liouville measure. We will just look at the expected moments of Liouville balls. How does it work more precisely? Well, I think on this slide there will be quite a few formulas, but I will explain them in words. So, on the Euclidean side, we will just define the normal Euclidean Minkowski dimension, and we just it's more convenient to do it using a fixed tiling. So we take a dyadic tiling of our domain. We look how many little squares intersect with our set of interest, and then we look for the power of the side length, so that if you take into account each square that's interacted to this power, then you will get then the sum will be of order 1. And this will give you a way to define a dimension. So you can do the same thing on the quantum side. Again, you take your set, you look how many little dyadic squares intersect this set, but now instead of taking a power of your metric dimension, you take a power of your Liouville measure. This you call the kind of the quantum Minkowski content, the size of your set under the Liouville measure. Then you take the expectation and you ask for which powers does it actually give infinity, or when is the phase transition from infinity to 0. So this is the formula. I will change the side so you don't have to look on the other side, on one side all the time. Using this definition, you can state and prove a KPZ relation. And what is this KPZ relation? You take a compact subset in your domain with Minkowski dimension dm, and then its expected quantum Minkowski dimension satisfies this quadratic relation. Given everything that I have told you so far, you can actually already see that the proof is really putting everything just together. Well, what do we know? We know that the Euclidean set has that the Euclidean dimension is Tm, so the number of balls that will intersect this set is just r to the minus Tm. On the other hand, to calculate the Liouville content of this, we just needed to take each little ball and calculate its expected moments. This we know how to do, this I explained. And now, if you want to find the whole expected quantum Minkowski content, you just sum this together. You sum these little Liouville balls over all the squares, and you get the following. You see that this will have change in behavior exactly when dm and q are are related by this quadratic formula. So this is the easiest KPZ relation. Now, if I know the scaling of the balls, I can then, of course, give you the KPZ relation also for the contour and flow lines. How does it work? Well, again, this time, you know, I look at my SLE curve. I know its Euclidean dimension. And now I guess I ask how big is its quantum content. And the relation you get is not the usual KPZ relation, but with a little change in the quadratic term. What can you conclude? You conclude that the usual KPZ relation does not hold for the flow lines or contour lines. Actually, the quantum dimension of these flow lines is always below the one predicted by the KPZ relation. But of course, it wasn't actually predicted by the KPZ relation, because everyone knows that the KPZ relation should hold only for field-independent sets. So here I would want to make the comment about whether this is surprising that we have a different KPZ relation, and I have two answers. The first answer is this is not very surprising, because really you expect the behavior to be different. You have chosen very specific set of your measure. But there are things that I found surprising. And what did I find surprising personally is that, for example, that we get exactly this relation. The form of this relation was a bit surprising for me. And the other thing that was surprising was that it's always below the prediction from the usual KPZ relation. I think that you know, no one could have said beforehand as easily. No one could have said that there is really no value of kappa and gamma, so that you don't have the usual KPZ relation. And maybe I should just point out what's on this graph as well. Here I have fixed some certain gamma, so some certain Liouville measure, and I've given the quantum dimensions for different kappas, for different SLE lines. Are there any questions so far? If not, I will actually tell you now what the work behind was. And formulated this way, all the work is actually in determining the scaling of Liouville balls when you put these balls on the flow lines or contour lines of the free field. So let me remind you what we are looking for. We are taking a ball that intersects the SLE curve in the Gaussian free field coupling, and now we are trying to look for the moments of the Liouville balls. And I already actually gave you the formula, so we already know what we are looking for. How does it work? Basically, it will be in two steps. The more technical step is determining actually somehow the winding. You remember that in this flow line coupling, you took your SLE path, and then to find the Gaussian free field, you put a zero boundary Gaussian free field in the slit domain, plus you added some harmonic correction term. And really getting good grips of this correction term means exactly determining the winding. And as soon as you've done that, you just somehow incorporate it in your Liouville ball estimates and do some more calculations. I will mainly concentrate in the rest of the talk on the first part, but I will just tell you a few things for the second as well. So how do you do the scaling estimates? Well, the winding is not defined on the curve. It will blow up. So actually you can't just take the ball and do all your calculations as easily. You will need to do a little trick. You will need to look at a Whitney type of decomposition. So what is a Whitney type of decomposition? In your domain, you cover your domain with say dyadic squares that don't intersect, that cover the whole domain, and that crucially have the following property. If you look at the side length of any square that you use, then it's basically the side length is of the same order as its distance from the boundary. So it really incorporates the the geometry of the domain. And what we do is we actually determine the scaling of Liouville measure for each of these each of these witness squares. And if we are done with that, we use this to give both upper and lower bounds for the scaling of peak squares that actually intersect the curve. There is some work to be done there because you want to see that you are not losing anything, and you want to make sure that you actually get tight bounds. But most of the work is now in obtaining the scaling of these witness squares. And let's see what we actually need. Loosely written, if you try to then calculate the Liouville mass scaling of a witness square, you see such a formula. And here, this is the winding term. So what you notice that you want to determine the exponential moments of this winding under some conditioning. And the conditioning is that the square is actually a witness square. And you can simplify things a little bit so that the special conditioning will be just conditioning about the point, the central point in your square. So in some sense, you will just condition the central point of the square being on some distance from the curve, and you want to ask how the exponential moments of the winding look like. So this will be the rest of the talk. So I will be interested in the winding of the caudal SLE curves. So winding was actually already studied in the very first paper on the SLE by Sham. And what did he study? He actually looked at the radial SLE and he really looked at the geometric winding. How many times does my SLE curve go around the point 0 up to intersecting a little disk of size epsilon? What did he find? He found out that this is described by a Gaussian that has variance minus kappa logarithm of epsilon. So what did we study? That was slightly different. In our case, we fixed some point in the domain. We fixed some little annulus around this point, and we conditioned the SLE curve to just intersect this annulus. And the question was, how many times does it wind around the point? And we used a slightly different dimension, a slightly different definition of winding, which is given by the argument of the derivative of the uniformizing map. But this should be asymptotically the same. This is actually proved also in the fourth imaginary geometry paper in the radial case. Let me also point out that this was, of course, long ago predicted by Duplantier, who basically, I think, knows all the calculations related to SLE. And you can see that there's a little difference with the radial case, and this somehow you can think of intuitively as the fact that you are putting two arms together. So what's the precise theorem we proved? Well, I stated here for kappa less than or equal to 4, it actually holds up to 8. We fix a point. We condition the conformal radius of the point to be of a certain size. We look at the curve, really the whole curve, and we determine the exponential moments under this conditioning up to multiplicative constants. So this is quite strong, and from this you can actually do further calculations, which we've been doing with Fredrik Wiklund a little bit. And for example, you do get the upper bound for the winding spectrum, and so on. It would be very exciting to do the almost sure winding spectrum, and maybe we can steal some knowledge from MIT to get there. So I will tell you something about the proof of this. So the first step is to use the radial parametrization, which means that you will actually fix the point. You don't want the point to move all the time. You fix the point at 0. And you parameterize the time so that it's given by minus the logarithm of the conformal radius. If you do this, and this is actually well known, it's in the paper of Beffara, lots of papers of Laurer. If you do this, then your problem will be actually reduced to studying a diffusion. The diffusion in the interval 0 to 2 pi, and the conditioning, what you need, will be just conditioning this process to exit the interval during some fixed time interval. And how do you see winding from here? Winding will be just somehow a functional of this of diffusion. You just need to actually integrate the cotangents of this diffusion over the time. And this same diffusion actually has been studied in many papers as well. It was studied in the papers of Sheffield, Schramm and Wilson, in papers of Laurer, Werner. So it's a known diffusion. Now, what happens with this diffusion? Well, you know, if you look at this diffusion, then actually what it wants to do, it wants to exit the interval more or less straight away. What we are doing here with the conditioning is that we are really forcing it to live longer. We are asking it to pair with us and stay for longer. And asking this actually intuitively is if it actually in the beginning wants to die and now you ask it to live for long, it's more or less asking it to really be immortal and live on forever. And it comes out that this is where you get the right estimates from. You just look at the diffusion that's conditioned to survive forever. You calculate, you look at the exponential of the winding, you put in the formula I gave on the last slide, and you do a calculation of exponential moments of Gaussians, and you get the formula we were looking for. Now, of course, the problem is that the conditioning you give is not exactly this. You don't condition the process to survive up to forever. So what you will need to do, you will need to somehow argue that up to some time they look similar. So there are several ways one could take up this problem. Well, one way is to look at try to reduce your diffusion to the ideal world using martingales. So you consider a martingale so that if you weigh by this martingale, then the weighed measure will actually be the measure of the ever surviving diffusion. You know actually what this martingale is. This has also been studied quite a bit. And then you have several ways to try to get information from this martingale. So one of the bounds you can get from it quite easily. The other bound seems harder. I don't know how to do it. So instead of taking this approach, I decided to push through directly. What do I mean by that? Well, you can actually write down the diffusion equation also for your conditioned process. You see, it won't look exactly like the process that was conditioned to survive forever. There's an extra term, there's some error term. And now, if we were looking for winding, then we were integrating this cotangents term over a long time interval. So we would really want to say that this error term, even when integrated over time, doesn't matter. And it comes out that you can do it. You can show that the error term is somehow minus exponential in time. And so when you integrate, you will be able to bound it. And doing this, your work will be kind of reduced to the following. You will show that in some part the diffusion really acts like the diffusion condition to survive forever. From there you get your main term, and then there are some annoying little intervals you need to handle to get the rest, to get the result. I will very shortly also tell you something about how you actually then do the analysis. So what do you do? Well, again, first you just calculate. You calculate the error term for the error term, and here the phi 0 is just the leading eigenfunction of the generator of your diffusion. Where did I put the eraser? So you calculate this, and on the other hand, you know that the probability of exiting at some interval can be given as a series expansion. So, for example, the probability that you will just live until some time t, you can write as some series expansion using the eigenfunctions of your generator.
Can you use white chalk?
I can, if I find it. Yes. Now I'm in the corner. Oh. And if you plug this in, you will find that you will actually need to prove some regularity estimates on the other eigenfunctions. You know the first eigenfunction precisely, but you don't actually know how the others behave. You don't have exact formulas for it, and maybe you could get them using hypergeometric functions, but I actually went down and showed by hand some estimates on this. After you do this, you are actually okay, because for the rest terms you can just use probabilistic arguments. So let me just tell you something which I would be interested to do next. One is, as I pointed out, doing the winding spectrum in more detail and trying to find the almost sure spectrum would surely be a nice aim. And the other thing is I would like to make more concrete the questions I had about the Gaussian free field. I would like to see, understand it better and understand the Liouville measure better, and maybe you can somehow do it also using these beautiful couplings. So I have finished quite early, but that's it.
Any questions? So when you do the coupling with the CLE4, and what happens when you don't use the SLE but the CLE? You got this.
Well, for the CLE4, what you do is it's basically the same. I mean, if you look at the CLE couplings, then this is also just like a boundary. So there you can basically do the same calculations.
One question? Just because I'm not sure I understood. So when you try to compute the winding, in this chordal case, so this integral, with cotangent.
Yes.
Not just an expectation that it will behave like this constant times t. It really is almost surely it will behave like that, right? So I'm not sure. Can you summarize what is the missing ingredient for what is preventing you from going further in?
From doing the almost sure spectrum, you mean?
Yeah. Basically.
Well, there it's the correlation between winding terms. You always get a upper bound on spectrums by by just the first moment estimate, but to really get an almost sure estimate, you need to understand how winding at different points behaves. And this I really don't know how to do.
So, using the same kind of techniques that Vincent used for the...
I would prefer the coupling with the Gaussian free field to somehow localize your behavior and then do something. It's
it would be right to use the GFF.
yes, yes.
Anything else? More questions? Yes.
When you calculate the Laplace transform of the winding, you say it equals epsilon to some power, and
Yeah.
in the notation there, is that means this estimate is up to constant?
Yes, exactly. So here you mean? Yes, this notation means up to some constants, and these constants you can pick uniform if you take lambda less than some lambda 0, and for all kappa up to 8. So I stated it for up to kappa 4, but you can do it exactly up to kappa equals to 8. Yeah.
You did not say much about your KPZ-like formula, the one with the extra factor.
Yes?
Because you moved down to windings, could you return to it?
I can, certainly.
Right.
This one? Yes. Well, it's beautiful. You can see that it reduces to the usual KPZ formula when kappa is 0, which you would expect because it's just a straight line, or when kappa becomes 8.
Well, my question is, where does it come from?
So the first term is basically what you would have if you do things on the boundary. So the first thing, the linear term always somehow comes from the boundary scaling of Liouville balls. Now this term somehow comes from the scaling of Liouville balls, the more probabilistic part there. And when your circular average process is just a Brownian motion, then this term comes from the exponential moments of this Brownian motion. Now this seems to hint that with winding everything is still nicely Gaussian, but the variance is just smaller, and it's exactly smaller by this factor here. So basically how I see it at least is that either in the Gaussian free field, on the Liouville case, just your Liouville balls they don't scale, they scale as a different log normal variable, and this is making it precise what the different means. And for me it's it's kind of an interesting question whether one can somehow characterize what kind of KPZ relations you can actually have in the Gaussian free field. Are they all going to be exactly of this form, or I don't know. But this is naive.
I have one maybe stupid question. Do you know one measurable set for which the usual KPZ relation holds?
Measurable?
Yes.
Okay, so I can give you, well, one which is I don't have a proof of, but which is quite sure, and which I find a little funny, is that you look at the square. Now you look at the line that exactly divides the Liouville mass into 2. And I would claim that KPZ relation for this line is the usual one, because it doesn't really matter what happens locally. And of course you can think of other things where which are even more cheating, where you take information of the Gaussian free field here to determine the set here, and then the KPZ relation will hold. So it's just as long as you don't really change things locally, it will hold. But with local things, I don't know. Maybe you can build up something. You take good contributions of each type of thick points, but I don't know how to do.